So Rohan is a senior software engineer at Lyft. He's been an individual contributor for 4+ years, working on all things related to AWS, Golang, and data. He brings a wealth of experience with a BS in computer science from Georgia Institute of Technology. He's done internships at Microsoft, Amazon, Lyft, Manhattan Associates, and Raytheon. Great to have Lyft here for the first time. Looking forward to this, Rohan. The floor is yours.
All right, we can get started. Hi, everyone. My name is Ron Varshini. Thank you for the introduction, Jim. Just to reproduce, I'm a senior software engineer at Lyft, and I'm here to represent our company to speak to our homegrown feature store's purpose, improvements, capabilities, and more. Before we begin, I'd just like to thank my teammates, current and former, for the incredible work that we've done so far in this space. Devin Mittal, Janice Lee, Yigal Castle, Mahip Manani, Prem Sandosh, Inday Shankar, Anirudh Datkar, many more. If they're in the call, thank you so much for everything, and plenty more soon to come. With that, we can go ahead and get started into the presentation. So I'll just read a portion of the presentation abstract here for posterity, just to set expectations on what we can expect to be covered. Lyft Feature Store is a core infrastructure component in our data platform, optimizing the management and deployment of ML features at scale, centralizing feature engineering, ensuring uniformity across models and workflow by streamlining feature creation, storage, all in the hopes to see it in model training and inference. So we hope today we'll be able to demonstrate the role that it plays in empowering all of our engineers at Lyft to develop service components and models effectively, and including for future AI and LLM applications. So before we get into the minutia of the system and all those little fancy details, it's important to set an expectation for the importance that it plays. Who are our users and what do they do? How important are they? As it turns out, very important to say the least. So here's just a short list of 5 of our teams, their purpose, and the impact that they drive. So first, the fulfillment team. They house machine learning models to match drivers to riders. They generate and rank those rider offers when they get the options, and it's empowering those services in parallel. The orchestration platform is working on rider and driver incentive programs. They launch machine models for batch campaigns to be able to target them, and they produce incremental driver hour engagement and growth. Those are the main metrics that they generally tend to look at. Pricing team, very self-explanatory. The Insight team is our fraud detection platform, potential blocker for fraudulent activity, both real-time and retroactively. The team works very hard to understand new patterns of fraud that come, and there's been very interesting niche edge cases where sometimes they have to look backwards and to see potential violators of such activity. And the market expansion team is our comms platform that builds audiences for targeting marketing messages, seeing who the specific type of folk that might be most likely to benefit from specific campaigns. So they're the ones who are driving our rider and driver engagement for existing users and hopefully increasing our ride count and revenue. And as a good reminder again, this list is just a subset of dozens of our use cases across Lyft. Each of them utilize our product for similarly important functions across the entire rideshare stack. So now that we at least know what some of our users look like, we can start to explore how our product is designed. The shortest way to describe that is we are a platform of platforms. And I know this is a very large architecture diagram, so we'll just zoom in on a few sections of it to make it a little bit more digestible. So first, we have our batch features. A customer might come and say, hey, we have existing Hive data tables. We want to design features from it. So what we say is, hey, you can go ahead and set up configuration files for your features in one of our repositories. There will be another Python service cron that reads those configuration files and automatically generates Airflow DAGs out of it. These generated DAGs come right out of the box with compatibility for feature discovery, data quality checks, and generate both offline and online data for the users. The offline data gets stored in Hive, similar to the source tables, and the online data is sent for storage to DS features. What is DS features? We have that as a shorthand for data science features, but it's essentially our optimized centralized wrapper over AWS data stores that would store that online data. DynamoDB serves as our backing store, and we have a write-through cache for lower latency retrievals in Redis, since then become Valky, and we have an OpenSearch integration for embeddings features. We have here the data retrieval from the customer perspective. They might have these batch features generating data, but then now they need to go and get that data for inference or for training. So they can utilize one of our SDKs, our standard development kits, libraries, in using either Golang or the Python languages, which are the two most frequent languages that we use across the entire fleets. They'll use these SDKs to send get or batch get API calls to the service. And in turn, DS Features fields those API calls, calls the AWS data stores accordingly based on the information of the features, and returns it to the customers in a friendly format for them to be able to use. With these SDKs, we also allow users to do CRUD operations, CRUD. So if they want to be able to do ad hoc reads and ad hoc writes on their own service side, they can technically have those real-time features used at that point. And finally, our streaming features follow a pretty simple paradigm. Flink applications will read analytic events that are sourced through Kafka topics. They perform their transformations. They send the data to our internal Beam application that would then be in charge of doing final touch-ups before sending it to DS Features with an API call for later retrieval and storage. So the diagram at least comes full picture. You can see batch features on the top right, streaming features on the bottom right, on demand with the bottom left, and then also the way the customer can interact to get the data through those libraries, which then calls our service to get the data from AWS online. Excellent. So that's what it looks like for a platform engineer. But what about our customers? What do they want to see? What do they need to see? What is their experience with this entire product? And to answer that question for the developer experience, we have to understand who our developers are. At Lyft, the folks who interact with our product take on many diverse personas. The two most frequent personas that we interact with are standard software engineers who drive service activity and generally have pretty broad experience in all things that we do at Lyft, and machine learning modelers who drive the need for features and design the models themselves. Sometimes an engineer could represent both personas. They have experience on both fronts and they're driving the things that both of those personas might need to achieve. Sometimes there's a team where they treat these two personas differently. There's individuals of each persona and they have very distinct responsibilities and they need to collaborate. It can vary from case to case. It can vary from team to team. But regardless of that composition, what we learned early on is that most of our frequently encountered personas, they understand SQL very well. And generally, they desire quick iteration on these features from the perspective of a changing and evolving SQL. So with that in mind, for our batch features, we developed a very clear predilection early on for Spark SQL as our engine. This is just a very simple screenshot of what a basic designed feature set could look like, where you're aggregating against a specific entity type, which user, and then you have different type of features that you might want to get against that, which write requested, write completed. Very basic example, but you'd be surprised that a lot of teams generally tend to derive insights from such simple features as these. Once they have that, they also want to be able to couple that with simple JSON configuration files to set different nuances to that feature behavior. So these configs can include metadata such as run-to-run carryover logic, the data listeners, ownership details, urgency tiering, and even explicit feature naming. And this is because it becomes important when we register this metadata for us to engage with monitoring and observability. It helps our customers who might need posterity of feature history when they iterate. What exactly did my feature look like 2 versions ago? Because we need to understand what was going on for specific feature retrievals at that time. It also helps us because we might potentially need to debug potentially buggy features where version to version, there may be something that went askew and we need to understand at a deeper level what the difference was between then and now. With that simple 2+2 of the SQL and JSON, it allows us to tap into our own homegrown solution for Airflow local development. We call it Kite. So one could perform feature validation, test their SQL running, test generated DAGs and run them, and even execute backfills of this DAG against previous dates, all within Kite without ever needing to merge their PR with the SQL and JSON into production, which lets them do a lot of prototyping and testing and validation before they even ever productionize it. This is all done using a custom CLI to improve that prototyping experience for personas who want to make these features with a lot more confidence. To improve feature discoverability, once those features are merged, once they're confident, they productionize it, and it starts actively generating data, we want people to be able to see their features, to understand that it's actually existing, it's generating data. This is something that you can start referencing and sharing with other people to get posterity on what's actually happening. So we utilize our Munson platform, which is our data discovery tool for everything at Lyft. The offline data from our generated DAG that was made from the JSON and SQL automatically takes that feature metadata and will tag it into a Munson so that users can search against that information. They can search for these features, and that helps us do all of the things that feature discovery can help us with: preventing duplicated work, reducing wasted engineering work, increasing shareability, increasing visibility, all these different benefits. Thus, we're able to solidify our very strong role in the machine learning model development lifecycle at Lyft. We take ownership in the data discovery, in the feature engineering steps that modelers and data scientists very frequently engage in. The majority of the remaining steps fall under the ownership of our MLP team. MLP stands for Machine Learning Platform. So for the other steps in this lifecycle diagram, they're the ones who generally take up ownership of those. But we collaborate with them very frequently to be able to make sure that we align on expectations for every part of this. So this seems like a promising setup and a customer experience then. Has it always looked like this? Someone might want to ask. And we can say for sure, certainly not. Over the last few years, we've chosen to prioritize efficiency and improved customer experience because we saw that was where the biggest amount of success for our customers came from. So that led us to take very strong steps. So first, we had to perform 2 migration hops to leave our original homegrown orchestration platform Flight to where it is today now, Astronomer. We had removed compatibility for alternative query engines that were weaker in terms of use case and in terms of relative margin. We had people using HiveQL and Redshift, but we saw that supporting these niche use cases ended up consuming most of our support bandwidth. And we saw that most of our base use cases that were using Spark tended to be where our most important teams in terms of PMM, in terms of use volume, that's where they were coming from, and it made more sense for us to focus our support towards those. After the right steps were taken across Lyft to make staging a more reliable environment, we were in turn able to unlock that capability for our own platform. So DS features, our entire batch generation process, staging, we were able to have a staging counterpart, which lets all of our users prototype and test features, not just in Kite locally, but then in non-production environments, which lets them do end-to-end integration testing a lot better. They might have data in both staging and production. They want to change business logic and test that against staging before merging it to production, which lets them have a lot more confidence in releasing not just important business logic changes, but also more urgent and sensitive features. We focused on what customers wanted, which was abstractions that made it easier to develop in Golang, which is a really large growing language of choice at Lyft. And we revamped our offline SDK used by Python engineers. And we tried to standardize capabilities and normalize activity that they generally tend to engage in. So that way we could align everything to a lot more of a standardized form and a more monitorable state. And finally, we're executing our organization's data contracts initiative. The goal for this is to enforce expectations on freshness, ownership, and quality. All 3 of these things become very crucial in the world that we're seeing now, where data generation and the amount of data that exists for us to get insight from, it's growing very rapidly. And we need to know what data to trust. So that trust becomes key. Data contracts is our way of being able to unlock that. And on the flip side, we started investing into our smaller base of features up to this point. Our batch features is our biggest family of features that we have at Lyft. The paradigm early on for our users was that freshness of a daily run DAG or even like weekly run DAG was enough to suffice for some of their use cases. But we're starting to see a lot more people who are able to see that the margin of freshness being reduced down actually gives them a lot higher of a benefit. So we developed a real-time ML pipeline interface via a library so that way streaming applications can start using them to generate streaming features with as low friction as possible. We've been seeing that this abstraction makes it easier for customers, which has been growing interest for people who want to develop with it later in the future, next year. We integrated OpenSearch as a compatible data store, and we've set embeddings as a specific type of feature within the entire code stack that we have as a compatible feature type. So if people want to be able to utilize our interface with embeddings, it's super easy. And we're seeing that this is unlocking the possibility for a lot of customers who want to potentially use us for that. And finally, we've made a lot of significant staffing investments into the streaming team to be able to develop it further. They've been able to unlock a lot of capabilities for our Flink apps to make them a lot more reliable, to make them a lot more cost effective, unlocking things that happen with the newest releases of Flink and being able to standardize expectations for all of the nearly 100 applications that we have across the company. And being able to staff the team even further means that for all the streaming applications that already exist making features and the ability to potentially onboard more customers who want to do that, we can now do that with a lot more confidence. So with such a large and important platform, as you can see, bloat and inefficiency can just be a characteristic that defines it. It can become very apparent very quickly. How do we optimize this platform? And for data generation, our answer was transparency. So we made sure that we had better monitoring that was set up against DAGs that were failing, streaming features and applications that were failing, failed tasks, and we tried to couple that with ownership tracking. That ownership metadata that we can then attribute to specific features makes debugging these things a lot easier. This unlocks the confidence to deprecate features that you think are being unused or incorrectly used. And then it just makes the clarity and transparency for a lot of things that are going on in the feature space a lot more clear. It's easier to have discussions and understanding what's happening with specific things. For data retrieval, how to optimize it for those aspects. Our customers generally just wanted one of two things: better latencies and better success rates. AWS data stores are the main source of latency in our data retrieval network call, and we needed to focus on protecting users from the pitfalls of having that as our paradigm. AWS data stores can technically be liable to transient failures that are unpredictable, 1-minute spikes where suddenly things are just failing without much reason. There can be very high P999 tail latencies, and AWS doesn't actually provide official SLAs on what you can expect from DynamoDB or their caches in terms of latencies. No P95 expectations, nothing. They have average performances that you can technically measure and set against based on your what you're able to see, but that's not something they can promise. So you have to focus on being as efficient as you can on your side to minimize those problems. So we try to be as lean as we can with everything we do in our network calls. We upgrade our cache version and our data stores as much as possible. We remove unnecessary fields in the retrieval code to make sure that decision-making is a lot quicker and doesn't require as many steps or potential parameters to decide against. We right-size our GS features service, the EKS pods, because every pod technically needs to connect to every single Redis node. And if you have double the pods, you have double the connections. And at some point, that number of connections, if it's super large, can actually cause all sorts of problems, as we've experienced in the past. So right-sizing the pods actually ended up being a great way to drive up stability. We improved retry and timeout policies within customer services and also our own, because every single time you prematurely cut off a network call due to an early timeout, that's an increase in success rate failures, but that can also get compounded because the service that the customer is calling from is calling us. We, in turn, are also doing our own retries and our own timeouts, and that can just potentially exacerbate and lead to a lot more failures. So right-sizing and taking trade-offs between retries and timeouts was able to help us drive the success rate further up. And finally, we increased our internal cache TTL as much as possible, both for the metadata that we use to make decisions about how to do feature retrieval, and then also for the feature values themselves while balancing against cost. You could technically put everything into a cache and just have a permanent cache data store, but that could be much more expensive. So we needed to figure out a trade-off for what we were willing to spend against versus what we think the greatest winnings for TTL and better latency retrievals were. with all of these adjustments and improvements, we were able to see some incredible trends for our platform. We cut the P95 latency experience down by a third over the last year. This was better for our on-call. It was better for our customers because every millisecond that you save gets passed down to them. And that can be something that gets experienced multiple fold for customers directly in the app after their whole call stack goes through this experience. We were able to grow our batch features, again, our largest feature family by volume, by 12% in count. And this was in spite of our very active feature deprecation efforts. We wanted to get rid of unused features and underutilized features as much as possible, got rid of hundreds of them, and we even still then saw this growth. This means that teams that use this platform have a positive experience, have positive value, and they seek to deepen their partnership with us. To pair with that statistic, we saw 25% increase in distinct callers over the last year. This doesn't mean individuals that are like coding and prototyping and developing models in Jupyter notebooks. This is distinct callers and production services that are doing active retrieval in significant volume of a lot of features. So this could be a separate service. This could be a facet within an existing service. Regardless, it's a fundamentally unique use case, and it sells the point that the entire company has a very increasing appetite for feature usage. Finally, we saw our aggregate activity increase by over 1 trillion in count. And this is on conservative extrapolation for the year. So I think this just serves as a reminder of the scale that all of our platforms in the feature space operate on. It's huge. And it's going to just continue to grow in the future. Because if this is the growth that we just saw in just this past 1 year, we can only imagine what could come in the years to come. So with that, I conclude my presentation. I hope that this was enjoyable and informative for everyone. Thank you to HopsWorks for having me. Thank you to everyone for listening in, and I'll take the remaining time I have for Q&A.
Fantastic, Ron. And thanks a million for a really fascinating insight into a lot of the details of your challenges and your solutions. I think it's been amazing. The last slide, that number is a huge number. And I'll admit, I plugged it into GPT just to figure out, like, what would this cost? And you had a lot of details related to, the dashboards you have for justifying kind of, I guess, to the business, you need to justify the value you're creating and so on. Is that something that you find is challenging with data platforms for AI, justifying the value and communicating that to the stakeholders so that they think this is really a great investment for Lyft?
Yes, so that's a great question. We, at some point about 1.5 years ago, we embarked on a discovery phase for our charter. We wanted to focus on seeing if there was actually any value for us to take our homegrown solution and vendorize it. And we wanted to see if we were happy with the solution, and also just understanding the impact that it has. So we spent almost up to a month at 3 engineers on the team doing just basically deep research. We reached out to all of our customers. We did interviews. We dug deep into our code. We dug deep into our metadata and our observability and tried to understand what the features were, who the people that we interact with are, what they think is important about us, etc. All of this research uncovered a lot of learnings about, I think, just like what's going on under the hood that we took for granted. And then even just colloquially from experience with our interactions with customers over the last 2 years, when things go wrong, you very quickly understand the value that customers seem to have in your product, what they're expecting, what the impact can be. And I think it became very clear that this is a platform that justifies its existence, justifies the need for engineers and the cost that it accrues. We also run pretty light as a homegrown solution since we do everything in-house. So I think because we're able to run it a little bit leaner, we can justify more resources pretty easily.
Nice. A couple of questions on in the Q&A. First one is, where can you find the slides? Do you mind is it okay to put the slides up on Slack, a link to them? Would that?
Yep, you can share the slides.
Okay, great. So the next one is, so Purushottam had a question about how Lyft is solving for feature evolution, but backfilling and versioning specifically. Do you want to take 1 minute to answer something on that?
Yeah, feature evolution. I guess at least within Lyft's domain, we've been seeing that the drive has been coming from what used to be very predominantly batch all towards streaming and embeddings. We've been focusing with initiatives right now on making sure that our current existing ecosystem is optimizing for proper healthy features and proper healthy data, because I think, like I mentioned in one of the last slides, the reality is the volume of features that are being generated and the calls against them is becoming so significant that we figured that it was best to focus on the foundational of work of the feature space to make sure that when we do make this type of hop to a really streaming heavy ecosystem to be able to empower LLM, AI, all these different types of products, we want to make sure that it's based in a world that's very strong in observability and
Yep.
transparency, because otherwise we don't want to create more problems for ourselves down the road. I think we've been seeing a lot of articles about how this AI revolution is coming with a lot of pitfalls that people weren't anticipating on transparency. And we really wanted to put that in the forefront of our mind before we get super ambitious with that work.
Brilliant. Thanks, Rowan. Thanks a million for joining us. And there's some questions that we didn't get time to answer. Maybe you can answer them in the Q&A or go on to Slack and people can ask you there.